Just finished the first half of the material for Mechanics of Materials. We have completed the midterm exam, and so your grade for the semester is half completed. In the last half of the semester, we're going to cover approximately the same amount of material. 3 of the chapters that we cover will be from the book. 2 of the chapters will be from handouts that I will give you later. But the material for today, Chapter 5, is purely from our textbook. So we'll begin doing that, and then when we get to the point where we need to do what are called combined loads, we will go off textbook, but I will provide that material with you before we get started. All right? So today, let's talk about Chapter 5, which the topic of which is the analysis and design of beams for bending. Now, we are going to revisit the idea of a bending moment, like we did in Chapter 4. However, now we are going to talk about the more general case where the bending moment will result in both a sigma, somewhere in the amount of my over I, or negative my over I, but also now we're going to produce some tau, although right now all we're going to talk about is the load V, which at some point we're going to develop tau, not tau average, but tau specifically as a function of that vertical load. All right, so basically when we start talking about beams, we normally discuss 3 different kinds of loads. Concentrated or point loads, distributed loads, and finally applied moments. Okay? So your authors begin by talking about the way in which a beam can be supported. And what this leads us to is the idea that before we get into the analysis of the internal responses of the beam, we always have to start with a good free body diagram. So in other words, we need to do our statics in order to determine what's going on in the supports. Now, one type of beam that we have talked about quite a bit is called a simply supported beam. And a simply supported beam has a fixed support at one end and a rolling support to allow for expansion and contraction on the other end. Another type of beam has the same 2 types of supports, but the fixed is at one end. Shouldn't put the little rollers there, it could go the other way, but we'll leave it like this. And a rolling support not at the end, but somewhere else away from the edge of the beam, and this is just referred to as an overhang beam. And then we have another type that is similar. One example of this would be a sign hanging from a signpost coming out of the wall. And this is referred to as a cantilever beam. And actually, this whole idea of something being extruded from the wall and bearing a load is referred to as cantilevered. So that's a pretty common construction term. Now, if we consider the dimensions, and everything that we do in this chapter, by the way, is very geometric. But if we consider the distance between the fixed support and the rolling support, whether it is a simply supported beam or an overhang beam, and the entire length of the beam as L in a cantilevered beam, all three of these types are statically determinate, meaning we can do an analysis of what's going on at the reactions in terms of what the load is borne at the reaction places using methods of statics. Now, there are other types of beams that are statically indeterminate. And one is called a continuously supported beam, which we just represent by a series of supports. A fixed support at one end and more than one rolling support throughout the beam. Another is a beam that is simply supported at one end and fixed support at the other end. So we have a simple rolling support and a fixed support. I was going to call that a 1 plus 1. The real name is a beam fixed at one end and simply supported at the other. And the other is referred to as a fixed beam, which means that we have fixed supports at both ends. Okay. Now, in the same sense that 1 through 3 are statically determinate, 4 through 6 are statically indeterminate, meaning that we're going to have some other type of analysis to aid us in finding what the reactions are at the supports. Now, having said this, we've talked about the types of supports of a beam. The next thing that we want to talk about are the types of loads. I'm trying to decide if I want to put this back up here or not. I'll go ahead and start here. Where we have a concentrated point load, I'm just going to draw a simply supported beam indicating this. You just have some sort of a load which we refer to as P on this beam, or perhaps two loads P on this beam. For a distributed load, you have something that is measured in load per foot or load per meter. And this is the way that we represent it, is with a series of arrows, meaning that you just have, you can't really say I've got a load here and a load here, but that you have this distributed load. One way that this works, or two examples of this, would be a beam that is bending under its own weight. The weight of the beam is continuous, right? And we need to analyze it in a certain way, but what we really are concerned with is the weight per foot or the weight per meter of that beam. Another can be an approximation, like if you have a bridge and continuous stream of traffic is going across it. You don't really take one car and follow it from one end to the other, and then the next car and follow it from one end to the other. You just get averages of what the traffic looks like over some period of time, rush hour or whatever. But we refer to the distributed load as small w, the terms of which are weight or load per unit length. Okay. And then finally we have moments. For example, if you have a cantilevered beam like this, and let's just say that you have a sign hanging down that has some weight, I'll just call it V, or let's call it capital W for the weight of the sign, what's going to happen here? Well, you're going to have a weight pulling up the wall. In other words, the beam is going to want to pull down, so the weight of the beam, if there's no other loads, is going to be, there's going to be a reactive load here, and there's also going to be a moment. In other words, this is trying to pull it down like this, and then we're going to have a moment that looks like this. Okay? So in other words, not only is the beam going to try to slide down from the wall, it's all going to try to pull out from the wall with this type of a motion, isn't it? So the wall has to counteract it with a load in the opposite direction. Or a moment, excuse me, a moment in the opposite direction. Okay. Now, the next thing that we need to do, and we have sort of avoided this for tau, so we're going to start doing this for V, and we're going to talk about sign convention. And trust me, the sign convention becomes excruciatingly important. Do you have a question?
No.
Oh, I was just wondering. I couldn't tell if you had your hand up or not. So the sign convention becomes excruciatingly important. And it is for moments, we've discussed the fact that clockwise moments are negative, counterclockwise moments are positive. And the reason for that is it corresponds to the right-hand rule, and also cross, which is the same as cross products of vectors, which is really what a moment is. For shear, or a vertical load, the sign convention is simply a convention, because a load in one direction is counteracted by a load in the other direction. Every single time. Has to be, or else something's going to move. However, we have to adhere to a convention in order to understand later if V's or taus add to each other or subtract from each other. So we maintain a convention, and I can't even tell you how strongly I would recommend that you follow this convention. Okay? If you choose to do it differently, I've never seen anybody able to do it effectively every single time, and there's no advantage. But if it strikes you as you're doing your homework, gee, this sign convention seems arbitrary, it is arbitrary. But if you always do it the same arbitrary way, you will develop a method of solving the problem where you're not going to be undoing your own work. Okay? So the sign convention depends upon, we're talking about this internal response. Okay? It depends on which side of the beam you begin on. Okay? So, if you have, for example, a situation where you look at a beam that's cantilevered and you cut it on the right. This is considered a positive moment, and this is considered a positive shear. So in other words, moment clockwise, shear down. Those are positive. And this talks about the internal response. If, on the other hand, you cut it this way, this is a positive moment, and this is a positive shear. Now you'll understand what I mean by this later, but I want to have it drawn out for you right now. So if you start on the left and you work toward the right in the same style that you read, and where you need to do an analysis of what's going on in the beam is at a cut on the right-hand side, V going down is positive, and a counterclockwise moment is positive. If, on the other hand, you start from the right, move to the left, and have a cut face on the left, V pointing up is positive, and a clockwise moment is positive. Now, the reason that we do this is because if you think about the actual beam, at some point, at some surface. You have moments that oppose each other, so the net moment is equal to 0, which is required for this beam not to rotate. So everywhere you go, the moment has to be equal to 0 in sum everywhere. And the same for the shear. If you have a V down on one side of a cut face and a V up on the other side of a cut face, the net V is 0, which is necessary for that beam to not split into halves or to split into parts. Because if they don't counteract each other exactly, movement will occur. This is required, I guess I would put, to remain in static equilibrium. So the question becomes, could I do it the opposite? Could I make this moment clockwise and this moment counterclockwise? Absolutely. Could I make this V up and this V down? Absolutely. There's no benefit to it, but if you choose to do that, I will support your choice. But if we just go along like this, you can follow along in the book, and you'll be able to do your homework problems, and your answers will come out to be the same as everything else. So, in terms of analysis, what we are doing is we're acknowledging that if we have a simply supported beam, that the load on the beam is not going to be the same everywhere, that the moment is going to be different from one slice to the next, and that the V, or the shear, is possibly going to be different from one slice to the next as well. So when we design, what are we really designing for? Are we designing for an average load? Are we designing for the smallest load? Are we designing for the largest load? That's right, exactly. Because once it fails, right? So it doesn't really matter what the average is. It matters what the maximum is. And so that's what we're getting at. So we do a geometric construction to hold this information for us. And the geometric construction looks like this. This is what your homework is always going to look like. You will draw the beam, and you will draw a free body diagram of that beam. And from that beam, underneath it, you will then draw a shear diagram of that beam. And underneath that, you will draw a moment diagram of that beam. Okay? So what I'm going to do today is to give you a couple of examples of what your homework solutions will look like. This is very different. There's very little equation math. This is visual math. Yeah! See? Exactly. So you have to do the math to find where you peak and so forth. But basically there's very, very little math. So I'm not going to go through, there are problems, the application problems 5.1 and 5.2, which are examples worked out in your textbook, are awesome, and we'll show you some of the ideas on how to make these work and what your final diagram looks like. But I would like to do some work for you as well, to give you some problems. Now, there's an interesting thing that I wanted to show you here on problems 5.1 through 5.6. And I'll go through a smattering of these for you. They don't give dimensions of the beam. In other words, they just call the length of the beam L. They call the distance from A to B small a, the distance from B to C small b. And they call like the load omega or W sub 0. I find this very strange because although these are very much more general, a lot of people get hung up on the ideas of what they call a literal equation, where there's no numbers in it. So I really prefer to start this with problems that have numbers, and then later we can make a generalization. So there's two ways that I do this. One is I put numbers in for problems 5.1 through 5.6, Or I look further down to see if there's anything that I can use that would give me the same information using, using numbers instead. So, and right now, they don't have the point load on a beam that I really like. So I'm going to work, the first problem that I'm going to actually work is 5.2, only I'm going to assign some numbers to this beam instead, okay? So when you look at CHAG or whatever solution you're having, you'll think, where did she come up with the numbers? Well, I'm just putting them in because I find and I'll do it both ways. How about that? I'll do 5.2 with some numbers in it, and then I'll do 5.2 with no numbers in it. You can see what it looks like. There you go. All right. And I have 20 minutes, so I should be able to do that. All right, 5.2. I am going to draw my beam, which is simply supported. And I am told that this is point A, and this is point C, and at some not centered but intermediate point B, there is a load of P. And that the distance from here to here is small a, the distance from here to here is small b, and the total length of the beam is L.
Oh.
Yes?
So this is basically just like algebra with no numbers.
That's right.
Okay.
Which are called literal equations, which are actually more symbolic, but literal because that means letters. So that is correct. So now you know, right?
So literal symbolic.
In our world, yes. Because when you deal with Mother Nature, pretty much everything is literal. All right, so I'm going to put this aside, and I'll work that with the letters, the literal form of the equation, after I work the explicit form of the equation. All right? So what I'm going to say is that I have a load P that equals to 500 kilopounds. And I have a reaction at A, a fixed support at A, a rolling support at B. And I'm going to say that the length of this beam is 12 feet long, and that the distance from A to P, or to capital B, is 5 feet. So what does that mean this other distance has to be?
7.
Good job, 7 feet. All right, so I'm going to work out this problem first. Now, I've already told you that what I want are 3 diagrams, the first of which is a free body diagram, whatever that is, free body diagram. There we go. All right, so the first thing I need to do to get a free body diagram is to determine what is the reaction at A and what is the reaction at B. Now I know that a fixed support beam is statically determinant, meaning that I can get those reactions using my methods of statics. So the first thing I can do is say summation forces in the y direction on this beam have to be equal to 0. I've drawn RA and RB up, which is a pretty safe bet because they're going to be pushing up against this negative 500 kilopound load, and because everything sits still, it has to equal 0. So that means that RA plus RB has to equal 500 kips. Okay, now that's true, but it's not enough. I still don't know what RA and RB is. If P were located right in the middle of the beam, it would be equally divided by symmetry, wouldn't it? In other words, we'd have 250 kips, 250 kips. We don't. Yes?
So you're just going to divide by 7 to figure out the proportion?
Basically, but in terms of statics, I'm going to do a moment equation about one of the points. Okay? So I'm going to say the summation of moments about some point, doesn't matter which, but I would choose one where there's reaction, because if my moment arm is 0, then the moment from that force is 0, right? So if I choose A, there's no moment from force A because there's no moment arm. So I'm going to take the moments about point A, set them equal to 0. this 500 kip pound, or kip force, produces a clockwise moment about A, so it's negative, right? And the moment arm is 5 feet. The reaction at B pushes up, so that produces a positive or counterclockwise force times the 12 feet. And those two moments together equal 0. So I can use that to solve for R sub B. R sub B times 12 equals 500 times 5. So I divide both sides by 12, and I get 2,500 divided by 12. And this is going to be in kilopound feet, and this is in feet. So my answer will come out to be in kilopounds. 2,500 divided by 12 is just over 200, right? 2,500 divided by 12, 208 and a third, 208.3 kilopounds. Okay? So if my reaction at B is 208.3 kilopounds, I can then find R sub A by saying R sub A has to equal 500 minus R sub B, which is 500 minus 208.3, which is 291 and 2/3, 291.67 or 0.7 kilopounds. Right. So now I have the material that I need to draw my free body diagram, which I'm going to draw over here. So one, a free body diagram looks like this. Reaction at A is 291.7 kilopounds. Reaction at B is 208.3 kilopounds, and 5 feet in, I have an applied load P of 500 kilograms. Okay. So that is my free body diagram. Now the next thing we need to do is to find the shear diagram. And the shear diagram is the internal response of this beam to the applied loads. And this is where that idea of cutting from the right or the left or the right, sorry, and determining what's going on inside of the beam using the sign convention that I just gave you, that's where that comes in. So, I'm going to work that on this. Now you work from the free body diagram when you do this. But I'm going to do the work up here because I want to draw this nice diagram down here. All right, so if I have the beam, every time I have a discontinuity, when I have a load applied or a reactive load, a support, I need to cut between there and there. So in other words, I need to cut, if this is 291.7 kips, my V, which I want to draw always pointing down, if I'm cutting from this way to this way, is always going to be up until 5 feet, is going to be responsive to the 291.7. So in the first 5 feet, when I say first, I mean from the left to the right. And now this is also, sometimes it's a lot easier to start on the right and cut to the left. I'm not fixed about it the way I am about my sign convention, but I tend to start on the left and work to the right. And if you do it the other way, sometimes there's one way that's infinitely better than the other, but in most cases not. So if I take a look at this, for the first 5 feet, the summation of forces in the y direction is equal to 0. So I have positive 291.7. Like I said, when I'm talking about internal response, I draw it downward as positive, but in this problem, it's a negative because if we're looking at the external reaction, it's pointing down. So those things added together equal 0, so 291.7 equals V. That means that my shear response for the first 5 feet is a positive 291.7 kips. All right, now this brings up another really important thing about shear. Shear tends to have humongous discontinuities. Moments, not as much. But shear jumps from 0 to big instantly and jumps from big to 0 or negative instantly. That's why shear concentrates, or this is a mathematical representation of how shear concentrates on connectors or fasteners. Okay? So when you have a support or you have an applied load, the shear becomes can become instantly huge. And that's what we're seeing here. We start with 0, and then where the support is, it goes instantly up to match that, and it stays at that match until we get to 5 feet. So what happens after 5 feet? We can say the next 7 feet. Okay? So what we have there is we have 291.7 pushing up. Now at 5 feet, we have 500 kips pushing down, and between there and the end of the beam, once again, because I'm cutting from here to here, I draw it like that. And once again, those three things have to add up to 0. 291.7 minus 500 minus V equals 0. When I take those two numbers, this, it turns out to be 208.3, but it's this minus this, 500 is bigger, so that's negative, equals V. So that means that here at this applied load, we immediately jump down to a negative 208.3 kips. Okay? Now, what do you notice about this value, 208.3 kips? It's the same as this, isn't it? So if I had chosen to cut from the right, what I would have would be this. I would have 208.3, and then between here and the next 7 feet, I would have some V, which I would draw like that. So then I would say 208.3 plus V equals 0, V equals minus 208.3 kips.
So if you cut from the other way, does it reverse the stress on it, or is it still the same?
That is a very good question. It reverses the direction of the shear in the sense that what we're really talking about is a shear plane that's being sheared like this. So if you look at it from this side, it looks like it's down. This side, it looks like it's up.
So I mean, like, if you went from the other side, would it be like a negative 291?
Right.
Or would it be the same thing?
It's the same.
Okay.
You see how I've done it here?
Yeah.
But it's tied into the idea that the sign convention takes that into account.
Okay.
Because when you cut, it's a great question, but when you cut this way, you draw V down as positive. When you cut this way, you draw V up as positive. So you're already taking into account the fact that what you're really talking about is a shear plane.
Okay.
Yep. Good question. All right, so here's my shear diagram. All right, what about the moment? Well, we remember that a moment is equal to a force times a distance, right? Moment is equal to a force times a distance. So for the first, I don't know why I changed color pens here. The first 5 feet, what do we have? Well, we have 291.7 kips pushing up, and we have a moment arm that goes from 0 to 5 feet. Okay, now I've already asked that if you cut this way, you call this a positive moment, right? So what happens? Here, the moment is 291.7 times 0 feet, which is 0. What is it here? It's 291.7 times 5 feet, isn't it? What is it everywhere here? The 291 stays the same, but the moment arm increases. So in general, what we have is 291.7 times the distance, x, which goes from 0 to 5, plus this moment is equal to 0. Okay? That's clockwise. And what about this one? This one is, or this is counterclockwise, so that's positive. This one, if we cut here, that's negative. This one's positive. Okay? So the moment everywhere is equal to 291.7 times x, where x goes from 0 to 5. And so you can see from this equation that it's linear. In other words, when I go from here to here, my moment starts as 0, and it ends up at this maximum value, 291.7 times 5, which is 291.7 times 5. That's 1,458.5 feet, or kip feet, 1458.5, and that it's a linear relationship. Okay. Now, and this would be, let me get my other pen here. Where'd you go? There you are. This is number 3, the moment diagram. Okay. Now, if you look at it, if you look at this geometrically, if you go from here to here, right here, the moment is going to have to be 0 again. And it's going to not, moments don't tend, unless there's an applied moment, they don't tend to be these discontinuities. But it's going to decrease in a linear manner from here to here. And that's the way the point loads act. Now, if I wanted to do the math on that, this is actually all you need for your diagram. But if you want to do the math on that, let's go to the next 5 feet. What you have is 291.7 here. You have a total of 12 feet to the end. And here at 5 feet, you have 500 kips. Okay? So everywhere from here to here, you have, when we cut here, and I put a positive moment here, I have 291.7, which is clockwise minus, times, if I call this x, 5 plus x, and then the 500 moment is 500 times not 5 plus x, but it's only it's operating from 5 feet in, so that's x plus m equals 0. And if you work out this math, you'll find out that you'll get the same thing, where I get m is equal to 291.7 times 5 plus x minus 500x. And so if I take the 291.7 and multiply it by 5, I get that value of 1,458.5. So m, I'm going to distribute this through, right, is equal to 1,458.5. Then I get plus 291.7x minus 500x. So I can bring these two together. 291.7 minus 500 is minus 208.3x. 1,458.5 equals m. And then I plug in this value of x from 0 to 7. And so at 7, when I plug that in, I find out that my moment is equal to 0 and that it's a linear relationship. Okay? So there's one purely graphical, one half graphical, and half mathematical way to find that value. Now, I did not have time to do the literal equation because these things always take me longer than I think they will, even if I'm writing just as fast as I can. So what I would like you to do I'm going to put this down as your assignment, but you don't have to do it yet. But the first problem will be 5.2 as a literal equation. But when we come back on Wednesday, I'll look at some different loading configurations and some different supported beams. And I'll do a couple of explicits like this, and then I'll add in the literals. Okay? All right. That's it for today, ladies and gentlemen. I will put that up. You don't have to get started on it yet, but I'll put that up as homework for Chapter 5, homework number 6.